covers the structure of the Earth's interior and is intended as supplementary material for my various physics classes. The four major layers of the Earth itself are, first of all, the crust at the top, below that the mantle, below that the Earth's outer core, and then down towards the center of the Earth's inner core. As you increase in depth, essentially three physical quantities increase as well, and that's temperature, pressure, and density. The temperature, pressure, and density of the various layers increases with depth. Okay, a little bit about the Earth's crust. The Earth's crust is actually composed of two different types. There is, first of all, what is called oceanic crust. Oceanic crust is primarily made of basaltic types of materials, minerals that are metal rich, and then therefore it's quite dense. And continental crust, which is made of largely granitic materials and is therefore less dense. The denser oceanic crust, being denser than continental crust, that is, floats a little bit lower on the mantle. Continental crust floats a little bit higher. Oceanic crust is usually pretty thin, usually in the neighborhood of about 5 to 10 kilometers thick, whereas at its thickest, continental crust, like at the locations of mountain ranges and so forth, is about 30 kilometers thick. Okay, the study of the Earth's interior by using seismic waves really begins with a Romanian geologist named Mohorovicic. Mohorovicic discovers the boundary between the Earth's crust and the mantle below. This boundary is named the Mohorovicic discontinuity, or just simply called the MOHO in his honor. Basically, what he discovered is that seismic waves refract at this boundary between the crust and the mantle below. They change speed and direction. So in discovering this boundary between the crust and the mantle below, Mohorovicic basically hits upon the key, the answer, if you will, to studying the structure of the Earth's interior by using seismic waves. Here's the basic idea. So seismic waves, as they propagate through the Earth's interior, if you recall from lecture, they are composed of two different types. There are P waves, which are longitudinal, and S waves, which are transverse. The longitudinal P waves travel faster than the transverse S waves. And then basically these two types of waves, they then reflect and refract at the various boundaries of the different layers of the Earth's interior. So by studying those refractions and reflections, we can then work out all the mathematical details of where the boundaries are located, what the layers are made of, their temperature, density, pressure, and so on, all of those physical characteristics. One thing that I want to mention, however, before we move on are the S waves, which are transverse and then therefore do not propagate through liquids. So this is how we know that the Earth's outer core is in fact a liquid, because S waves do not propagate through it. So then therefore, because of that, we know that the Earth's outer core is a liquid. We also know that the Earth's outer core is a liquid because it's the source of the Earth's magnetic field. Okay, a little bit of detail here about the upper mantle of the Earth that's directly below the crust. The upper mantle, the very upper portion of it, is in fact solid. And so then therefore, if you take the solid crust above and the solid upper portion of the mantle, this then results in what is referred to as the lithosphere. The lithosphere is broken up, however, into about 24 tectonic plates over the course of the surface of the Earth. And then once again, density and temperature increases with depth. The upper mantle is composed of rocks that are called peridotites. And then below that rigid lithospheric layer is a plastic, tarry layer called the asthenosphere. The asthenosphere flows very slightly, and this is what the tectonic plates are basically floating upon. And then as they grind against each other at plate boundaries, this then results in earthquakes, volcanoes, and so on. Okay, so a little bit about the asthenosphere. The asthenosphere is a plastic or tarry-like substance that flows kind of much like a toothpaste, and it flows very slowly, usually on the average only a couple of centimeters per year. But that's enough, basically, to drive plate tectonics then at the surface of the Earth, giving us then all the geological features that we see with respect to volcanoes, earthquakes, and so on. So the lithosphere, the lithospheric plates, are able to move due to convection currents within the asthenosphere. This mechanism ultimately drives plate tectonics. Okay, a little bit about the lower mantle. As you can see, the lower mantle extends quite to a large depth. It's composed of these types of materials. It's denser than the material that's above it. And then as you go down into the lower mantle, it becomes semi-rigid due to the high pressures, and then temperature and rigidity increases with depth. Okay, and then we get to the Earth's outer core. The Earth's outer core is a hot, electrically conducting liquid, and this is where convection currents occur. This then generates a dynamo effect along with the Earth's rotation to produce the Earth's magnetic field. This later is not quite as dense, however, as pure molten iron, which indicates the presence of lighter elements. The boundary between the outer core and the mantle is the source of convection within the Earth's mantle itself, by the way. This is what's driving plate tectonics. This boundary between the Earth's outer core and the mantle is referred to as the D layer. Okay, and then we have the inner core. The inner core of the Earth is basically composed of very heavy metals, primarily nickel, iron, and some other heavy metals as well. And then even though it's hotter than the liquid outer core, it is in fact a solid. And the reason why is because the pressure when you get down towards the center of the Earth is so enormous. So this process is referred to as pressure freezing, where basically the liquid, if you will, of the outer core is then frozen in place as the inner core. And this is then what results in the solid inner core. Okay, and then lastly, here's an interesting hypothesis that was proposed by a geologist in the 1990s. A man named Herndon hypothesized that the center of the Earth may actually contain a ball of solid uranium, maybe about 5 miles in radius. This uranium, under enormous heat and pressure, would actually be a natural fission reactor. Evidence for this includes the byproducts of fission reactions that are present in the mantle material that makes it to the surface of the Earth during volcanic eruptions. And there also is a precedent for this. This person right here in this photograph is pointing at a uranium ore deposit near the surface of the Earth. And this uranium ore deposit actually is quite dense. In fact, it was so dense billions of years ago that for a brief period in the Earth's geological history, this was actually a natural uranium reactor, which was actually pretty close to the surface of the Earth. It's named the Oklo reactors. And this kind of set the precedent for Herndon's hypothesis that there just might be a natural fission reactor at the center of the Earth. Okay, so that concludes this brief screencast covering some of the details here of the Earth's interior structure.